Okay, good afternoon. We had looked at three-phase circuits in the last class. In fact, we had completed that. So I am planning to discuss a few problems on three-phase circuits. So I'll start with the first problem, which says a balanced delta connected load having impedances 27 angle minus 25 degree ohm and a balanced Y connected load having impedances 10 angle minus 30 ohm are supplied by the same three-phase ABC system with VCN equal to whatever is the value that is given. Obtain the line currents for all the three phases. That is what is being asked. Okay. So let me try to first of all take up this problem. So problem number 1. It says this is the three-phase line, let us say, and there is a delta connected load like this, and there is a star connected load. So this is one of the delta connected loads and the value given is 27 angle minus 25 degree ohm. This is what is given as the per phase load. The other one is a star connected load. So this is the star connected load which is going to be connected somewhat like this. So this is the star connected load. So now this is, let us say this is connected here and the second phase this is connected here. So let us say this is connected here. And the third phase, let me say I am taking it from here and connecting it here. So this is a balanced system with the one star connected load and one delta connected load. And the Y connected load value is given as 10 angle minus 30. And one more thing that is given is the supply voltage per phase voltage VCN is given to be 169.8. So this is given as VCN equal to 169.8 angle minus 150 degrees. So I should be able to write VBN as 169.8 minus 150 plus 120. So that will be minus 30 degrees. And VAN I can write as minus 30 plus 120. So that will be 90 degrees. So I'm going to have 169.8 90 degrees volts. All of them are going to be volts. Now we can do it in two ways. If you want, you can directly look at what is the delta per phase current and then you can try to convert that into line current. But that is a roundabout way. So we had already seen delta to star conversion. So in delta to star conversion, we used to write this as if I want a particular lines, RA or RB or RC, whatever I want. So I should be able to write this as RAB RBC divided by RAB plus RBC plus RCA. So if I want really B, RB, which is a star. So let me name this as, for example, A, this is B, and this is C. If I want what is the equivalent star from B, then I should be able to use this expression. And if all of them are equal, I'll get star impedance will be equal to 1/3 of delta impedance. Because this is going to be, if I say some Z value here, so I will get Z times Z divided by 3Z. So I will have essentially Z by 3 as the star impedance. So that's what I'm writing here. So compared to delta impedance, The star impedance will be 1/3. So correspondingly, if I convert this into star, so star impedance in this particular case will be 27/3, which is 9 angle minus 25° ohm. This is going to be the star impedance. Okay, so now I have to actually take parallel combination of these two star impedances. So I can think as though these are the three lines. Now I'm going to have the three lines and I'm going to connect one star connected load, which is from delta. I have converted that into star. This is one star connected load. I can have one more star connected load, which will be like this. These two are in parallel. And similarly, I can have one more in parallel here. And similarly, I can have one more in parallel here. So these are going to be the parallel combination. Okay, so I can write as though the impedance 9 angle minus 25 and 10 angle minus 30 are in parallel with each other. 9 angle minus 25 and 10 angle minus 30 are in parallel with each other. So I had to find the parallel combination of these two. And I can write as though this is connected right across the three-phase supply, and then I can calculate the line current. That's not a big deal. Okay, so 9 angle minus 25 happens to be 8.157 minus J 3.8 ohms. And 10 angle minus 30 happens to be 8.66 minus J5 ohm. Okay, so these are the two impedances. So I should be able to calculate, if I may call this as Z1 and I may call this as Z2, I should be able to calculate Z1, Z2 divided by Z1 plus Z2. Z1, Z2 will be 90 and this is 30 and 25, that will be minus 55. Divided by Z1 plus Z2, I have to add the real parts and I have to add the imaginary parts. So when I do that and convert, I am getting here 16.817 minus J 8.8 ohms. So these two have to be now, this also better to convert that into polar form, then it is easier to divide. So this comes out to be 90 angle minus 55 divided by 16 point.
Ma'am?
Yeah?
Ma'am, I'm kind of confused. What you did was first you changed from polar to rectangular, right? Of
This
the
is polar
9,
to rectangular here. Yeah.
and then you found the parallel resistance in each one.
No. I am trying to calculate the parallel combination of these two. I am trying to find out the parallel combination of Z1 and Z2. So you have to do Z1, Z2 divided by Z1 plus Z2. That will be the total parallel combination. So I have to first of all multiply these two. Always multiplication is easier done in polar form. Addition and subtraction are easier done in rectangular form. That's why I wanted rectangular as well as polar form. So I'm multiplying these two. This will be 9 multiplied by 10, that is 90. 25 plus 30, so that will be essentially minus 55. Both of them are negative, so they will be additive, so minus 55. And Z1 plus Z2 is 8.157 plus 8.66, that is 16.817. And here 3.8 plus 5, that will be minus j 8.8. So Z1 plus Z2 is this. Okay, got it?
Yes, ma'am.
Now this 16.817 minus j 8.8, again, unless I convert it into polar form, it's not going to be easy for me to divide this by this. So I'm going to convert this into polar form. When I convert this into polar form, it happens to be 18.98 angle minus 27.62. This is what I'm getting. Okay. Now, when I want to get the overall, so this is 90 divided by 18.98. So it will be slightly less than 5. So that is 4.742. That's what I'm getting. And 55 plus minus 55 plus 27.62. So that comes out to be minus 27.38 degrees. This is going to be the parallel combination of Z1 and Z2. So I'm going to have again and again Z1 and Z2. The parallel combination of these two I have found out. So this is Z1 in parallel with Z2. Okay. Now that I have the impedances and I have per phase voltages. So I should be able to find the current. I have per phase voltages. So let's write 169.8. So VAN equal to 169.8 angle, I think 90 degrees. That's what we got. I'm trying to check. Yeah, 90 degrees. So I should be able to write VAN is this. So IAN is going to be 169.8 angle 90 divided by 4.742 angle minus 27.38. Okay, and that comes out to be 35.8 ampere magnitude with 117.38. This is the amperage. I can directly calculate VBN from here because it's balanced load. The magnitude will not change, but the angle I have to do with minus 120. So 117.38 minus 120. So that will be 2.62. So I will have VBN, so IBN to be the same 35.8 ampere with an angle of 117.38 degrees minus 120 degrees. So that is going to be 35.8 angle minus 2.62 degrees ampere. ICN has to be further 120 degrees away. So 35.8 minus 2.62 minus 120. So that will be minus 122.62 degrees ampere. That's it. So let me look at the second problem from here. A balanced delta connected load with impedances 10 angle minus 36.9 degree and a balanced Y connected load are supplied by the same three-phase ABC system with VCA. Please note this is line-to-line voltage. And 141.4 angle 240 volts. So if I know VCA, I should be able to definitely get what is VAC. VAC will be exactly 180 degrees away from this. Okay. So I should be able to tell that 240 minus 180 or 240 plus 180. Either way is fine. So 240 minus 180 is 60. So 141.4 angle 60 will be VAC. And IB is already given. So what are all the impedances of the Y connected load? So it is just the converse problem of what we did just now. So what we did just now was we were given, so in problem number 2, What is given is 141.4 volts angle, angle 60 volts is VAC. So if I want VAN, what should I do? I have to first of all divide this by √3, because we always talked about V line equal to √3 times V phase. That is the first thing. So magnitude I can get directly. How will I get the angle? So if I say that this is VA and this is VB and this is VC. Okay. Now what is being given is VAC. So if I write this is VC, so minus VC. So I should be able to write VAC like this. This is VAC. This is VAC. And this will be 30 degrees. And this will also be 30 degrees. Okay. So minus VC will be lagging behind VA by 60 degrees. Whereas VAC will be lagging behind VA by 30 degrees. So I should have VAN to be, if this is 60, right? So this angular position is 60. That is what is given. And this is another 30 degree addition. So obviously this position is going to be 90 degrees. If I say this is 60, this will be 90, only then this will be lagging behind by 30 degrees as compared to VAN. So I should write this as 90 degree volts. Is this clear? Unless you know how the vector positions are located, you will not be able to immediately infer the phase angle. So here, by the phasor diagram, I should be able to infer that VA should lead VAC by 30 degrees. That is the reason why I'm having this as 90 degrees. So this is 90 degrees. Is this clear? Okay. So now what is being asked is, they have given one delta connected load whose impedance values are given. And they have given another star connected load whose impedance values are not given. So this star connected load impedance values are not given. These are not given. Okay. So what is being asked is, what is Z2 if Z1 is given and the current is given? IBN is given. IBN is given. So if IBN is known, from VAN we should be able to write VBN. What is VBN in this particular case? VBN will be 141.4 divided by √3 angle 90 minus 120. So this will be minus 30 degree. Now, if IBN is also given, then I can say VBN by IBN is equal to Z1 by 3 in parallel with Z2. Right? Because Z1 I am converting into star. So from which Z2 can be calculated. Is this clear? Any questions? Any questions? So if this is clear, let us go to problem number 3. So let me read out first of all problem number 3. 3 identical impedances are connected in delta to supply a 3-phase supply of 400 volts. The line current is 34.65 ampere and the total power taken from the supply is 14.4 kilowatt. Calculate the resistance and reactance values of each impedance. Please note the voltage is given as 400. The line current is given as 34.65 ampere and the power is 14.4 kilowatt. So root 3 VL IL cos phi, we should be able to directly say that is 14.4 kilowatt. Okay. So let me try to work out this problem. So let's say this is problem number 3. So the first thing that is given is 3 identical impedances connected in delta. So I should say that the power is given to be 14,400 watts, which is equal to root 3 VL IL cos phi. And that is root 3 multiplied by 400 multiplied by IL. IL is 34.65 ampere and cos phi, from which definitely cos phi can be inferred. So cos phi comes out to be 0.6. Okay. And obviously sin phi is 0.8. If cos phi is 0.6, sin phi is 0.8. Okay. Now I should say V phase divided by I phase should be equal to Z. If I talk about this in terms of magnitude, I should say V phase magnitude and I phase magnitude. I should take. V phase magnitude is the same as V line because it is delta. So we are going to have V phase equal to V line, but we are going to have I phase equal to I line by root 3. So V phase I can write here as 400. And I phase I should be able to write this as 34.65 divided by root 3. So that is going to give me magnitude of Z. I think this comes out to be 20 ohm. Okay. So if this is 20 ohm, I should say Z cos phi will be the resistance and Z sin phi will be the reactance. I hope you remember the impedance triangle. We said that if we are having R, IR is like this, IX is like this, right? And then we are going to say these two added together will be IZ. So if this is phi, which is the impedance angle, and if I say this is IR and this is IX magnitude, obviously this is phi. So this is going to be, R is going to be Z cos phi and X is going to be Z sin phi. So that is how we get Z cos phi is R and Z sin phi is X. So 20 multiplied by 0.6, which is 12 ohm. And this is going to be 20 multiplied by 0.8, which is 16 ohms. Any questions on this? Any questions? Okay, so let's try to look at what is the fourth problem. A 3-phase 4-wire system supplies at 400 volts, supplies power to the motor. That's what it means, at 400 volts and lighting at 230 volts. So at home, whatever we have as lighting supply, that is all 230 volts. Your single phase bulbs, what you buy from the market, all of them are rated for 230 volts. If the lamp in use require 70, 84 and 33 ampere in each of the 3 lines, what should be the current in the neutral wire? If a 3-phase Y-connected motor is now started taking 200 ampere from the line at a power factor of 0.2, what should be the line current in each line and neutral current? Find also the total power supplied to the lamps and the motor. So this is the total problem. So it says that we are going to have 400 volts as the supply line voltage and 230 volts as the single phase voltage. Okay, and all the loads are star connected according to what is given. So let's try to do this. So here what is given is V line is 400 volts and V phase is 230 volts. Okay, and there are three lamps connected. And each lamp is taking from one particular phase. So one lamp is taking 70 ampere. Let's call this, I'm just assuming, it's not given clearly, but I'm going to assume that this is from A phase. So this is A phase. And the other one is B phase, which is 84 ampere of current. And C phase, which is going to give me 33 amperes of current. One thing you have to realize is, because lamps are generally resistive load, the current should be in phase with voltage. Current should be in phase if it is a normal incandescent lamp. So in that case, it will be resistive. So current should be in phase with the voltage. So if it is connected between VAN, if I assume this is 0 degree, this will be minus 120 and this will be plus 120. Clearly. This is how I'm going to have IA, IB and IC lamp current. So I should say lamp current IA. And similarly lamp current IB. And this should be lamp current IC. Now, in this case, I should write I neutral is equal to IA plus IB plus IC. So when you add, please convert these into rectangular form. Then it is easier to add. So I would say convert into rectangular form and add. Okay, I'm not doing it. I'm going to ask you to do it. Please do it. The second portion of the same problem says a motor is started which takes 200 ampere. How much is it? 200 ampere at 0.2 power factor lagging. So I can calculate what is cos inverse of 0.2. That is the power factor angle 5. Okay, and it is lagging, so I have to write this as minus 5. Okay, so I should write this as minus of 78.46 degrees. So I'm going to write, if I look at each of them, this is a star connected motor as well. So it is somewhat like this. I'm going to have the three phase lines and all the three phases are connected to, first of all, lamp. So one lamp is connected between this and neutral. So if I show a neutral line, this is the neutral. So one lamp is connected between A phase and neutral. Another lamp is connected between B phase and neutral. And the third lamp is connected between C phase and neutral. So this is A, this is B, this is C, and this is neutral. And I'm going to have a motor. I'm going to just show the motor like a circle. And this is going to be connected from here. This is C. And this is going to be B. And I'm going to connect A. So A, then this is B, and this is C. All three phases are connected like this. Now what is being asked is what is the total current here, and total current here. So I should add IA total equal to 70 angle 0 plus I should say 200 angle minus 78.46 degrees. That will be the total IA current. IB total will be 84 angle minus 120 plus 200. What should be the angle? Please remember, compared to this angle, B phase angle should be minus 120 degrees further. So 120 plus 78, 198. So minus 198.46 degrees. Okay, fine. And similarly, I should have IC total. What is the C phase current total? So IC total will be 33 angle 120 plus 200 angle 1 minus 1 minus 78.46 plus 120. I have to add this to 120. So in which case this comes out to be 41.54 degrees. All of them, of course, the unit will be ampere. So I have to calculate these and put it together, saying that each of them is one phase current. Now the power input to the motor will be root 3 VL IL cos phi. So that is going to be root 3 400 multiplied by 200. Cos phi is 0.2. So this is going to be the wattage. Okay. Whereas power taken by the lamps will be VAN IA plus VBN IB plus VCN IC. Magnitude simply because it is resistive load. So 230 multiplied by, I can simply say 70 ampere, and second thing is 84 ampere, and the third thing is 33 ampere. So this is the total wattage. Okay, so that comes out to be some 43.01 kilowatt, whereas this comes out to be something like 27.712 kilowatt. Any questions on this?
Ma'am?
Yeah.
What will be the current in the neutral wire from here in the load? Will it be IA, IB, IC total or?
Yeah, because motor will not contribute to any neutral current. Motor will be basically IA plus IB plus IC of the motor. If I say IAM is the motor current, IBM is the motor current again, ICM is the motor current in C phase, this will be 0 because this is a balanced current. This will not contribute to neutral current. So to the neutral current, what has contributed was only the original lamp has contributed to neutral current, and that will not change. That will not change because you have not really included any other unbalanced load. If you include some other unbalanced load, that would have contributed to neutral current further. Okay, is that clear?
Yes, ma'am. And here in the power, you added 70 and 84 and 33 together into 230, right?
Yeah.
Okay. Okay, ma'am. Like, shouldn't you have done 200 the angles?
See,
IC total,
the
IB
thing is,
total.
you normally write VI cos phi as the power, right? V as the RMS value, I as the RMS value, cos phi is the angle between V and I. And because the lamp loads are resistive, cos phi is 1. That's what we said. These are all scalars. No complex number here. Directly RMS values. V RMS, I RMS, cos of the angle between V and I, if at all there is something. Here they are in phase. So cos phi is 1. That is the reason why I could take it as it is. Had it been, something like there had been some cos phi value and it had been different in different phases, then I could not have done this so easily. Because it is resistive load, I could simply add that. Got it?
Ma'am, here there was cos phi, right? 0.2, but here.
That was only for motor. That's why I said power taken by the lamps alone. I have not taken this 200 ampere into consideration at all here. So I calculated this separately and I calculated this separately. This is only resistive, whereas this is motor. If you had to take this separately, for example, if you had taken the total current, IA total, IB total and IC total, you could have done it like that. You should have done VAN, IAN, cos phi. Cos phi will be whatever is the summation of these two. Okay? The angle, whatever you get after calculating the summation. So it is like touching your nose with a lot of roundabout route. You can directly touch your nose. So you can directly calculate balanced output for the motor and the power taken by the lamps because they are only resistive in nature. So you didn't have to do anything special here. Directly voltage multiplied by a current will give you volt ampere as well as wattage because cos phi is 1. Okay?
Ma'am, so if we are asked like total of the motor and lamp, we should do it like that.
No, even now you can just add the two powers. Powers are scalars, average values, scalars. I can simply add these two. No problem. If I am asked what is the power taken by only A phase, then also I can say 230 multiplied by 70 plus whatever I have calculated as root 3 VL IL cos phi for the motor divided by 3. That's it. That will give me power taken by only phase A. Phase A loads. Still it will work. Because this is balanced, there is no problem. Whereas even if this is unbalanced, we have only V multiplied by I because cos phi is 1. No problem. Okay?
Yes, ma'am. Understood.
Yeah. So let us look at problem number 5. A 3-phase 3-wire ABC system with a balanced load has an effective line voltage of 200 volts and peak line current. Please note peak. So RMS, if I want, I should divide it by root 2. 13.61 ampere with a phase angle of 30 degrees. Obtain the total power. You can directly do root 3 VL, which is 200, IL, which is 13.61 divided by root 2 cos phi. Cos phi is cos 30.866. That's it. You can directly calculate root 3 200 multiplied by 13.61 by root 2 multiplied by cos 30. That's it. That should give you the power. Okay. So please verify whether you are getting it correctly. The next one, two balanced delta connected loads with impedance 20 angle minus 60 and 18 angle 45 respectively are connected to a 3-phase system for which line voltage is so and so. Obtain the phase power of each load. Obtain the total line current with both loads in parallel and compute the total power and compare with the sum of phase powers. You are given two impedances, both are in delta, 20 angle 60 and 18 angle 45. First of all, you can calculate the parallel combination of these two. That will be the effective impedance. So that is effective impedance per phase in delta connected fashion. So from that, you should be able to calculate what is the value of the current taken by each of the phase. Current taken by each of the phase will be 212.1 divided by the parallel combination of 20 angle 60 and 18 angle 45. Okay. So that will give you what is the current taken by each of the phases. Of course, one will be at angle 0, the other one will be at angle minus 120, the third one will be at angle plus 120. So when I write actually the expression, I should write it somewhat like this. Let me write this problem number 6. So I should write if Z1 equal to 20 angle 60 minus 60, sorry, and Z2 equal to 18 angle 45 ohm. So Z1 parallel Z2 I can calculate. Okay, fine. So once I calculate Z1 parallel Z2, I can use, let us say this I am calling as some Z3. So I should say what is given is VBC is 212.1 angle 0. So I should be able to say I phase 1 should be equal to 212.1 angle 0 divided by Z3. Then I should be able to say I phase 2 should be equal to 212.1 angle minus 120 divided by Z3. And I phase 3 will be equal to 212.1 angle plus 120 divided by Z3. Okay. So I can directly calculate now I phase 1, I phase 2, I phase 3 will be exactly equal in magnitude. Phase angle will change. That's all. Now I can say 3 multiplied by V phase multiplied by I phase multiplied by cos phi, where cos phi will be whatever is the difference between the phase angle of the current and phase angle of the voltage, which is 0. The same way in this particular case, phase angle of the current I will get for I phase 2 and phase angle of the voltage, which is minus 120. So that will be uniform in all the three phases. So I will get what is cos phi without any difficulty. Okay. So this will give me 3-phase power. Please note I have calculated phase current, not line current. If I want line current, what should I do? I should actually say either I phase 1 minus I phase 2 or I phase 2 minus I phase 3 or I phase 3 minus I phase 1. Either way is fine. Please remember this is what we are talking about. This is the delta connected load and I'm calling this as I phase 1. And I'm calling this as I phase 2 and I'm calling this as I phase 3. So if I want the overall current which is going, let us say, in this direction, for example. So that should be I phase 1 minus I phase 2. The same way if I am talking about a current that is flowing in this direction, this will be I phase 2 minus I phase 3. And if I'm talking about something going in this direction, that will be I phase 3 minus I phase 1. Seventh problem. Obtain the reading of 2 wattmeters in a 3-phase 3-wire system having effective line voltage of 240 volts, a balanced delta connected load impedances of 20 angle 80 ohm. That's what is given. Okay, so impedance is 20 angle 80 and line voltage is 240. So let's say problem number 7. So this says 240 volts is the line voltage or the voltage and delta connected load and that is 20 angle 80. Okay. So if I want to calculate the magnitude of phase current, I should say 240 divided by 20. If I just say what is the magnitude, this is going to be 240 divided by 20, which is 12 ampere. So correspondingly, if I want to know the magnitude of line current, it will be √3 times 12 ampere. So I got the line current. Please recall what we did in 2 wattmeter method. So 2 wattmeter method, we said each of the wattmeter is going to give me line voltage multiplied by line current multiplied by cos of 30 plus phi, line voltage multiplied by line current multiplied by cos of 30 minus phi. That's what we said. Okay. So if I say that this is line current, so wattmeter 1 reading is going to be VL IL cos of 30 minus phi. The other one is going to be VL IL cos of 30 minus phi. It's okay if one of them is phi plus phi, other one is minus phi. Doesn't matter what we call as W1 and what we call as W2. It doesn't matter really. Okay, because you are going to connect 2 wattmeters in 3 lines as the case may be. So you don't know exactly how the readings are going to come. So in which case, I can write this as phi is 80 degrees. So I have to write this as VL is 240, IL is √3 times 12 ampere, and the cos of 30 minus phi is 30 minus 80. So cos of 50 degrees, cos of minus 50, which is same as cos of 50. So this is going to be this. And the second is going to be VL, which is 240 times √3 times 12 multiplied by cos of 30 plus 80, which is 110 degrees. So please note this will be a negative reading, whereas this is going to be the positive reading. So in 2 wattmeter method, for certain values of phi, for example, if it is greater than 60, definitely I'm going to have one of them as negative and one of them as positive. So if phi is phase angle is greater than 60, then one of them will be positive and one of them will be negative. One of W1 and W2 will be positive and the other will be negative. Okay, fine. Anything? Any doubts? So if I look at this particular problem, 8th problem. A 3-phase ABC wire, 3-wire ABC system with line voltage equal to so and so and line currents equal to so and so, find the readings of wattmeters in lines A and B, B and C, and A and C. This must be 218.0 degrees. Maybe this is wrong. Please make sure that you correct it properly. 218.0 must be. So please note this particular thing works even in the case of unbalanced. So you have to take basically whatever is the angle between the particular voltage and the particular current. That is, please note what we said in wattmeter, 2 wattmeter method was something like this. We are going to connect one current coil, let us say in A phase, and the voltage coil is connected between A and B. So what we are going to do is VAB multiplied by IA multiplied by cos of the angle between VAB and IA. This is what we said as one of the wattmeter reading. So this is how you will infer the wattmeter reading. So the wattmeter reading, what you infer, will depend upon across which 2 points you have connected the the load, the voltage coil, and across through which point you have connected the current coil. In this particular case, this is carrying IA and this is carrying VAB. So that is why I have to take the angle between these two. On the other hand, let's say if I have connected in B phase and I have connected the voltage coil between B and C, for example, then I should say that VBC IB cos of angle between VBC and IB. This is going to be my wattmeter reading. Got it? So the wattmeter reading heavily depends upon between two lines, which two lines I have connected the wattmeter and in what way I have connected it. So here it will be VAB, IA and cos of angle between VAB and IA. This is how it is going to be.